What is the charge on the 1.5 microfarad capacitor? This one. So first of all, this capacitor is connected in parallel. Reason being that there is a parallel line here and there's a parallel line here. Then we have the capacitor here and capacitor here. So if you remember that, you now need to remember that the voltage on a parallel capacitor is the same, but the charge is different. And how do you do that? By finding first of all the capacitance here. So when you find the total capacitance, multiply with the voltage, you get the charge. Then let's do it. So the question, we have something like this. Then we have another one like this. Then we now come and have remember we said that on a battery, the big part is positive, small part is negative. So we have this to be 12 volts. So if we were to calculate this now, to see the capacitance C total will be given by C1 plus C2. So C total, and the answer is in coulomb. So that means we have to convert to coulomb, so to microfarad to farad. So remember we said that 1 million microfarad is equals to 1 farad. That means that 1.8 microfarad is equals to x farad. So cross multiply. So we now get 1 million microfarad times x farad is equals to 1 times, so it's equals to 1.8 microfarad times 1 farad. So you see that since I don't know x, I can say divide both sides by 1 million. I want to get x, I divide by the coefficient of x, microfarad, divided by 1 million microfarad. This will cancel this. So x farad will be equals to this microfarad here will cancel this microfarad here. So that I have 1.8 farad divided by 1 million. Remember that the microfarad here has been taken care of by this one, so it's just 1 million. So by the time you do, this is the something that's in 1.8 times 10 raised to the power minus 6, because this is a denominator. So by the time you do 1.8 times 1 million, you get x farad equals to 1. So you get 1.8 times 10. So yes. Okay, I'm supposed to do division. What are you doing, Bitcoin? It's divided by 1 million. So you get 1, 2, 3, 4, 5, 6. So you get this far. So that means that that's for the, so x farad, which is equals to the first capacitance C1. So without doing this, to do the second one without stressing yourself, it will simply be the same as saying 1.5 times 10 raised to the power minus 6 farad for C2. So I'll now have this to be 1.8 times 10 raised to the power minus 6 plus 1.5 times 10 raised to power minus 6. So by the time you do 1.8, by the time you do 1.8 times 10 raised to power minus 6 plus 1.5 times 10 raised to power minus 6. If you do it well, you get 3.3 times 10 raised to power minus 6. That is the total capacitance. Yes, you know that this is this. So it's just the same thing as saying 1.8 times 1.5. Yeah? Yes, 1.8 times 1.5, then doing times 10 raised to power minus 6 plus 10 raised to power minus 6. So there you have it. So you've gotten the total capacitance to be this. Then the voltage, remember I told you that if, for example, I have charge of Q plus here, charge of Q minus here, and I have charge of Q plus here, and I have charge of Q minus here, notice that the voltage that will run will come here, go to this, and as the voltage is going to this one down here, this same voltage is going to the one up here. That is why we say that voltage for parallel is the same. Is the same. Is the same. So now to get charge, I know that charge Q is equals to CV. So I will simply say Q on the first capacitance will be equals to C1V. Why I did this one is so that we can use it to prove your answer. Why Q on the second one will be equals to C2V. So that means that for Q1, I should be having 1.8 times 12. And for the second one, I should be having 1.5. Okay, first of all, times 10 raised to the power minus 6, then times 12 voltage, then times 10 raised to the power minus 6 times 12 voltage. So that Q1 is equals to, so by the time we do 1.8 times 1.8 times 10 raised to the power minus 6, then times 12, you get 2, that is 1, 2, 3, 4, 5. 2.16 times 10 raised to the power minus 5. Then when you do 1.5 times 10 raised to the power minus 6 times 12, you get Q2 to be equals to 1.8 times 10 raised to the power minus 5. So by the time you do this now, you can now see that Q total should be equals to Q1 plus Q2. That is, Q total should be equals to 2.16 times 10 raised to the power minus 5 plus 1.8 times 10 raised to the power minus 5. So let's do it. 2.16 times 10 raised to the power minus 5 plus 1.8 times 10 raised to the power minus 5. So you get 3.96 get 3.96 times 10 raised to the power minus 5 coulombs. So let's check if our answer is correct. So we'll do QT should be equals to total capacitance times voltage. So QT should be equals to, we got total capacitance to be 3.3 times 10 raised to the power minus 6. So to verify our answer, we'll say QT equals CT, so times 12. So 3.36, sorry, 3.3 times 10 raised to the power minus 6 times 12. So you get the same thing. So you get QT is equals to 0.0000396, which is equivalent to, this is equivalent to 3.96 times 10 raised to the power minus 5. Yes, so coulombs. So that means we are correct. And if they ask us now the charge, that means that the charge on Q2 that the question asked us is simply 1.8 times. So our answer is, let's check the option there. So our answer is option D. Option D is our answer. So D. Option D is our answer. So if we know this now, let's answer the second question. The second question says, find the equivalent capacitance of the arrangement in figure 3.15. So they say we should find the equivalent capacitance, but see what we'll do. We'll find the equivalent capacitance, we'll find the charge, and we'll find the voltage where necessary. So let me redraw it. Okay, I think this question I put it from the textbook. So let me go and find that page on the textbook. So let me redraw this one. Okay, so see, the problem with this question is that they did not give us the voltage. So they just want us to find the equivalent capacitance. So but I will still illustrate and do a situation where they put voltage, so that we can be able to solve this kind of question. This type of question is when they combine capacitors in series and parallel. So how to go about it is to simply have two things in mind. The two things you need to have in mind is that for series capacitor, total capacitance is given by you remembering that total capacitance is equals to 1 over CT. That is 1 over CT equals to 1 over C1 plus C1 over C2 plus dot to any number of capacitance, which means that CT is actually given by 1 over C1 plus 1 over C2 all raised to the power minus 1. You need to note this. You need to note this. And for parallel capacitor, C total is simply equals to the sum of the capacitance. So why for why for this one? This is simply CT is equals to sum of ratios of capacitance raised to negative power. Why is raised to negative power? Is because the 1 over the total capacitance, that power 1, that's 1 over total capacitance. When you make total capacitance sort of formula, the 1 will go and go up on the right hand side. So this one is simply sum of capacitance. So if I know this, I can now go back to this question. So I see that this is moving this way. So first of all, let's check the ones in series. So you can very well see that 5, let me call this C1, 5 microfarad. Then is in series with this and with this as well. So you need to know, let me call this one C2, let me call this one C3. This is 2 microfarad and this is 6 microfarad. So it's in series with it. Then, as it's in series with this one, it is also, yes, it is also, if you check it, in series with this 3 microfarad. But I will not go there. I will not go there. Let me take this one that is in series first and make it so that it will now end up becoming this way. So I will sum this up. I will sum these two that are in series up. So in series. So that means that it will simply be the same thing as saying 1 over CT equals to 1 over 2 plus 1 over 6. And this will simply be having 6 as the denominator. Because that's what they have in common when you have 2 and 6. 2 here, 1, 3, 3, 1, 1. So you have 6 here. So you can now see 6 here, 3. Then 6 here, 1. So 6 here, 3 times 1, 3. Plus here, 6 here, 6. It's 1. 1 times 1. So 4 over 6. And you know that 2 can go here to get 2. 2 can go here to get 3. So I now have 1 over CT is equals to this. And by the time you check this out, I don't want to turn this. By the time you check this out, you see that this is going to be 1 over CT equals to 2 over 3. They can cause equality sign. So that CT comes to 2 CT and 3. Good. So I now have 2 CT, sorry, 2, the T here is for showing you the charge. That is, sorry, showing you the capacitance, that is total capacitance equals to 3. So by the time you do this now, you see that you now say divide both sides by 2. So the total capacitance here is simply 1.5 and is a microfarad. So that means that now that I've gotten this 1.5 microfarad, I can go back here and redraw this. Can go back and redraw this. Can go back and redraw this. And notice that as I'm redrawing this, this is in parallel with this. These two are in parallel. So let me redraw. So now that this is the same thing as saying I have 2 new circuit diagram will now be like this. I know your mind will want to tell you to put it somewhere here, but if you put it here, you've now made this one that is parallel to this one to be out. So 3. So the minute I do this now, this one, let's say this one I started with, let's say I call this one C1, and I call this one C2, C3, and I call this one C4, capacitance 4, C5, C6. Remember I said I C total for that one. So the CT for that one, that CT that I put there is now going to be that this is actually, because the last capacitance here is C6. That means that the new thing I formed here, which is this 1.7, is going to be C7. So let's call this C7. C7. It's supposed to be C7. Any new capacitance you are finding that is not the last one, C is the next one after what you are given. If you like, you will understand it. You are paying attention. Right. So remember, this is our circuit. So C7, I've gotten C7, but notice that C7 now is parallel to this. I need to form something in between this, and we know that whenever circuits, notice I'm not completing the diagram so that you see where we're at. Whenever I have circuits in parallel, their capacitance is simply by summing it up. So, okay, if going at it the first way is a big deal or an issue to you, what you do is to do parallel arrangement and series arrangement. So parallel arrangement will simply be you looking out on this. Now you see that if you look at this very well, from this end, these two lines are parallel, and on this side, these lines are parallel. So let's pull it out. So it's the same thing as saying, if I pull this thing out this way, I'll have this and this. Forget the fact that I did not close, I closed it, it's not supposed to be closed. So that means that this and this are in parallel. And then if I pull it out on this end, sorry, if I pull it out using this end, this measurement this way, and then using this arrangement, so this is even better because it will reduce the circuits and make it less complicated. So you can see that 2 microfarad, 6 microfarad, 3 microfarad, and 2 microfarad. You can see that these are in parallel. So everything here, they are in parallel. Everything here, they are in parallel. This will be a better way to arrange it. So that I can now say, if I want to find these two now, I want to find these two to make it one, I'll simply say in parallel it will be C1. Let's say I call this C1. Let's say this is, let's say what I have here is C1, C2, C3, C4, C5, C6. So I now have C1 and C5. So to get the C7, anything you are getting as capacitance, the next one after what you've counted on the main circuit is the next capacitance. So C7 will simply be equals to C1 plus C5, which means that C7 will simply be equals to 5 plus 45. So C7 will simply be equals to 50. So if you want to draw it now, the minute you join two capacitors that are in parallel, it now becomes something like, let's say, as I'm going this way now, I can now come and see that it is actually in this place. So I now have 50 C7. So it has replaced it. Once you solve for circuits in parallel, you see it as something that is now in series. So let's say I come over here. These ones that are in parallel, all these ones that are in parallel, let me now do it. So let's say that I have C8, the next one. The next one, this is a better approach. So the next one now, it will simply be equals to C8 will simply be equals to, this is C2, and notice something before I do for C2. Notice that these two are in series. So these two are in series. They are in series. So I have to solve for C2 and so first of all, let me solve for this now. So C8 will simply be the ones in series. So it will be 1 over C8 equals to 1 over 2 plus 1 over 6. And by the time you finish doing it, I think we've solved it before. By the time you solve it well, everything there will give you 1.5. So C8, everything, if you solve this as a mathematician, you get 1.5. I know why I'm putting mathematician, because you have to learn how to solve. So that is C8. Let me check it again. Don't want to solve it. So you get it. So that means that the diagram now will move from this now to be the sentence saying I have this and I have this. So it will simply be 1.5 here microfarad as C8. So then you have this one that is here 3 microfarad. Then you have this 2 microfarad. So they are in parallel in the sense that they have parallel lines in between them. So if I want to get C9, the next one C9, it will simply be the sum of everything here. So let me do it. So C9, so if you look at it, you see that it's even simpler than you stressing yourself doing all those ones that are doing you like headache. So let's say this one is C8 now. This is still C4 and this is still C6. So it will simply be C4 plus C8 plus C6. So C4 plus C6 plus C8. So C9 will be equals to simply be equals to 2 plus 1.5 plus 3. 2 plus 1.5 plus 3. 2 plus 1.5 plus 3. So it will simply be that C9 is equals to 3.5 then. So that is, if you remember, 3 plus 3 is 6. So 6.5 microcoulomb. Microfarad. What are you saying, coulomb? Are you okay? Microfarad. So this is it. So that means that you have been able to get this now. You have been able to get this. So if you want to draw the new diagram now that you've established this way, so you can see very well that if you do it this way, it is best doing it this way. Because notice that of all those things we solved that time, C10 that we are supposed to have, it helps us get the final thing. So that C10 we solved that time supposed to be something like this way. But because we are using a long process, we are running around getting the things we need and the things we do not need. So please, I will advise you, as a student that have worked with me through these solvings, and you've seen how we did it the first approach, when you just look at it and want to solve everything, and you now see how it goes. So it's best whenever you are solving a circuit problem, be able to break it down, starting with looking at it from the parallel side. So solve everything that looks like parallel there. By the time you finish solving everything that looks like parallel, then it is the sentence saying that you've been able to break the circuits down. So if you now want to get the total capacitance there, that's where you can now say, okay, bringing everything that you've done together, and you can now backtrack. So I can now say CT or C10, CT will simply be equals to, because everything now is in series. So I can now say, okay, it is, I did this and this together, it became 1. And what it became, what this thing became, is C7, shading 50, 50, 50. Then that is in series now, 50. Then I did this one, these two together. What it became this 1.5. But remember that the 1.5, we moved everything together to solve this. Yes, to solve this particular one. That give us C8, that give us 6 points, that give us 9, that is C9. So what I'm going to sum up for C total is simply C9 and C7. So by the time I sum up C9 and C7, and they are in series now, so it's now 1 over CT equals to 1 over C9 plus 1 over C7. So 1 over CT will simply be equals to 1 over 6.5 plus 1 over 50. 1 over 50. So you need to see this thing this way. I'm able to see it in this way because I know that I solved this one, broke everything down. It's entered in series. Then did this one to enter in series down here. But remember that everything here will move it together. When we solve something in parallel, we take it that it has now formed something in series. So I can say that this is the same thing as saying, if I want to show you the diagram, it's the same thing as showing it this way. I have this, I have this. Then I have something over here as my C7. As my C7. Then my C9, by the time I broke those things down, everything down, is the same thing as saying that my C9 is somewhere here. C9. So all these ones have been closed because we solved all the things parallel this side. So I got the last point starting from here to this point. Then we solved all the things parallel to this point. So C9 and C7. So the total capacitance in this now is C9 and C7. So that is what I'm putting together. And C9 is 6.5, C7 is 50. So by the time you do this, you now have 1 over C10 all over. Let me check the LCM. So I can do, let me approximate to have 1 over 7 plus 1 over 50. And I know that this is going to be something as saying 50 and 7. 7 is a prime number. So what can divide 50? 5 can go here to give me, yes, to give me 10. Yes, 7. 5 can also go here to give me 2. 2 here, 1. So bring yourself, bring yourself. So 7 here, 1, 1. So it's something like saying 50 times 7. Since they are not the same LCM, so all over 350. So into this, so it will have 50 plus 7 equals to 57 over, yes, 350. So I have 1 over C total equals to 57 over 350 crossover. So that I now have CT57 is equals to 350 divided by 57. This will get out. So total capacitance will simply be equals to 350 divided by 57, which is equals to 6.14 microfarad.